All right, so hello everyone. Thank you very much for joining us. I apologize for the delay. I'm going to hand this over to Professor Impey, and we're going to go ahead and get started. Thanks for joining us today.
Okay, welcome everyone to another live session for the online class, our last before the holidays, and we may have a break of about 3 weeks because first week of January, I and many in my group are going to Honolulu, Hawaii for the American Astronomical Society meeting. Yes, it's a hard life being an astronomer when you have to go to Hawaii in January. Of course, we live in Tucson, so January is a very nice month here too. Apologies to any of you who are dealing with snow, wind, and cold. Floor is open for your questions.
All right, thank you, Chris. The first question we have is from a live viewer. Alexis would like to know if rogue groups of asteroids or comets in interstellar space can clump together to form a planet.
Interesting question. So interstellar space generally is pretty devoid of matter. I mean, the mean density of matter in the space between stars is extremely low. It's about 1 atom per cubic meter, so really low density. And generally, when stars and planets form, they form in very particular places because of gravitational collapse. So it doesn't really leave much material left over. The most likely way that significant sized objects or material can be in interstellar space is when they're ejected from a planetary system, and that can happen. So it's possible for planets to be ejected. It's very unlikely, actually, for large numbers of smaller objects like multiple asteroids or multiple comets or smaller objects to be ejected in that way. But what could, of course, happen is that a single large object can be ejected, and in the process of being ejected, subject to tidal forces that essentially destroy it or break it into smaller pieces. So that is one scenario by which a significant sized object like a moon or a planet-sized rock could be ejected from a solar system due to a gravitational interaction, maybe by a nearby passing star or by a close interaction between planets in the system, could be ejected from the system and disrupted in that process, leaving a bunch of rocks or rubble in interstellar space. That being said, it's an unlikely occurrence, and there's also very little way for us to detect such tiny objects far from, for instance, our solar system.
All right, thank you, Chris. The next question is from Dennis Baller, who sent an email. And Dennis is interested in sort of the definitions of moons and planets. So in general, a moon orbits a planet, and planets are large and moons are small. But what happens if there is a big moon orbiting a small planet? When we start to, does this change the definition to something like a binary planetary system orbiting the sun? Is there a threshold for the mass difference? So, for example, are Pluto and Charon both dwarf planet-moon relationships, or it's more of a binary system? And what about Earth and the moon?
Yeah, it's an interesting question. Astronomers, like to classify things, but they really don't like to get too hung up on jargon and definitions, because the truth is the universe has offered enough diversity to us observationally in terms of moons, planets, stars, galaxies, quasars, whatever you like, that it's kind of dangerous to make rigid definitions, because then you're forced to relax them or alter them. So that's one issue, that we try not to make too many different definitions because they tend to get broken. The other is that definitions or taxonomy or classification by certain properties is not always a physical definition. So astronomers prefer to make definitions based on physics or astrophysics rather than just on the way something looks or appears or one property of it, such as its size or mass. So that being said, there are broad definitions and understandings of moon and planet. So in the simplest terms, a planet is something that orbits a star of any size. So it's an object that formed around a star, and a moon is an object that orbits a planet. And so obviously the general situation is going to be the planet is substantially smaller than the star, and the moon is substantially smaller than the planet. The question of how much smaller is arbitrary. So in our solar system, for example, the moon, our moon, the Earth's moon relative to the Earth, is about the largest mass ratio, or the moon is the largest fraction of its planet's mass as anywhere in the solar system. And that's about what we think is the largest situation. The moon, as we know, is formed by a collision, or as we are almost certain, was formed by a collision with a Mars-type object very early in the history of the Earth, which splashed off a bit of the mantle that then orbited the Earth to form the moon. So the moon is essentially a fragment of the Earth. Now, Charon is also a large moon compared to Pluto, and Pluto is a dwarf planet. And so technically, and according to planetary scientists, Charon is a moon. It's classified as a moon, not as a binary dwarf planet with Pluto. But then then the definitions get a little awkward. And the other thing that's going on with these objects is capture. So if the formation scenarios always have the moon being substantially smaller than the planet, and the planet being substantially smaller than the star. But if the object is captured, then they could be much closer in mass. And so as soon as you have a captured object, it's going to break the rules, or it might break the rules. And essentially, you have to find some way of knowing whether it was captured or whether it formed that way. And that can be a sort of a circular argument, because if we don't know the full range of formation properties, and it's very difficult billions of years later to know whether something was captured or formed coevally, then we have a problem. So that's a long and roundabout way of saying that there are definitions, that the general demarcations of moon to planet to star are pretty clear, and astronomers end up being fairly flexible on those definitions, because to not do so is to sort of risk breaking every definition you ever make.
Thank you, Chris. The next question is from an email. Pat asks, why is it that gravity is not instantaneous but travels at a finite speed, which seems to be the same speed as the speed of light? In other words, why is it that action at a distance of gravitational pull from the sun to the earth is felt with the same time lag as that of light? And what's the connection between light and gravity that produces this result?
Now, that's a very interesting question, because the truth is we don't know. We have not actually demonstrated with a simple physics experiment, it's not a simple physics experiment at all, that gravity propagates with the speed of light. That is a supposition of the standard model of physics, that the force of gravity does not exist instantaneously. The only argument that it would not be propagated instantly at too large distances is an argument for causality. Because if gravity could have its effect everywhere in the universe instantaneously, because remember, gravity is an infinite range force where the strength of the force goes down as the square of the distance, but that 1 over a square of a large number is never zero, that creates a significant problem of causality, and that's a profound logical problem for physics. So that is a logical causal argument why gravity should not propagate infinitely fast. The other argument, of course, is that in the laws of physics as we understand them and in relativity theory, the speed of light is the fastest way of any signal or information to propagate. And since gravity essentially is a signal or information, it's a signal that mass exists, then logically and according to relativity, gravity should be subject to that same speed limit. But remember, that's not been tested. That's a supposition, because relativity, special relativity, certainly was not formulated with gravity in mind. Physicists do continue to try to find new ways of measuring how gravity propagates through the universe, but no convincing test has yet shown its propagation speed. A sidebar on this, of course, is gravitational waves. So gravitational waves are disturbances in gravity, and we have pretty good evidence, because now we've detected gravitational waves from distant parts of the universe, that they do indeed propagate at the speed of light. In fact, the proof of that came with the very first detection of gravitational waves, where the arrival of the gravitational waves between two continental United States LIGO detectors was separated by 7 milliseconds, which is essentially the speed of light traveling between those two distant locations. So for gravitational waves or perturbations of gravity, or gravity changing and causing ripples in space-time, it does indeed propagate at the speed of light.
Thank you, Chris. The next question is from Daily Ardonaut, who's on with us live, who asks, is supersymmetry somehow related to the 8-dimensional model, or E8 crystal? And could any of this information be useful for a theory of everything?
So supersymmetry is not directly connected to the E8 formalism. E8 is a unification that is really in line with string theory, which tries to represent all the forces of nature in one unified situation of multidimensional space-time, typically 10 or 11-dimensional space-time. Supersymmetry is a sort of step along that road, but it's not the same thing. Supersymmetry tries to overcome the fundamental distinction in particle physics between bosons and fermions, that is to say, spin-zero particles with integer spin, or integer or zero spin particles. Photons have zero spin, other bosons have integer spin, and fermions, like electrons, which have half integer spin. So fermions and bosons behave in quite different ways, and supersymmetry is a way of unifying these different types of particles into a consistent framework where every particle has a supersymmetric partner, and so a shadow particle, if you like. Supersymmetry has been attempted to be tested by the Large Hadron Collider and has not actually shown any evidence that it's the way nature works. So supersymmetry, while it was a promising theory for simplifying physics, in looking for deeper level of unity in the proliferation of particles in the particle zoo, has not found to be the case yet by experiments and particle accelerators. E8, string theory, and multidimensional theories of everything are even further from experimental test. At least we have experiments that can test supersymmetry, and they've been found wanting, which is to say the simplest and most natural supersymmetry theories are essentially ruled out at this point. String theory is not ruled out because it simply hasn't been tested, because it pertains to energy scales or physical scales that are literally a couple of dozen orders of magnitude beyond which is available to experimental physics, and that's an incredible challenge to be able to test those theories.
The next question is from Jason Frankie, who's on with us live, who asks, why is it so difficult to test the validity of string theory? Do you think someday we can come up with evidence to prove or disprove it?
I think the reason it's difficult is because in the theory itself, you're dealing with energy scales and spatial scales that are inaccessible to experiment. So if you take the highest energy available to us with the Large Hadron Collider, that is, I don't remember the number, but it's something like 24 orders of magnitudes away from the energy that would be required to demonstrate string theory in the lab, which is maybe the best way of testing it of all. So you're not even on the ballpark. You're not even on the radar. It's just that far from being a physical experiment. So people are left with very indirect means of trying to test string theory, which are essentially that since the premise of string theory is hidden dimensions, those hidden dimensions are compactified, if you like, or only exist on an extremely small physical scale and an extremely high energy scale. There are some versions of string theory where there potentially are manifestations of those hidden dimensions that can appear without having to go to these incredibly high and unattainable energies. There's a lot of skeptics about those tests or those manifestations or tests, and none of them have been conducted successfully anyway. And that's part of what's fueled a kind of jaundiced reaction to string theory, where despite the beauty of the mathematics and the noble goal of unifying all of physics in a theory of everything, if you can't test it, it's not science. So that's not just me as an observer or experimentalist saying that. That's just how science works. And so the harshest statement about string theory is it's metaphysics or philosophy, that it's not physics until you can test it. It may be beautiful mathematics, but there's plenty of beautiful mathematics out there that doesn't apply to the real universe, and we don't call it physics either.
Thank you, Chris. The next question is from David Marshall, who's on with us live, who would like to know how far away and what is the most distant object that's ever been observed.
So there's a pretty active competition amongst observational cosmologists and astronomers to find the highest redshift object. So typically these the distance is measured by astronomers in terms of redshift, which reflects the expansion of the universe. So in the redshift definition is that the wavelength in the rest frame of the radiation relative to the wavelength in the observed frame, where it's stretched out by the expansion, is equal to 1 plus z, the redshift. And so if you have a redshift of 1, the wavelength is doubled or stretched by a factor of 2 between the wavelength of emission and the wavelength that we receive it after the expansion of the universe. And you can convert in an expanding universe model redshift into distance in billions of light years. The highest redshift objects at the moment, there's always a set of objects, quasars or very distant galaxies, typically seen through gravitational lensing to amplify their light. And this is always through large telescopes, the VLT or the Keck telescopes, 8 or 10 meter telescopes. The highest redshifts that are confirmed, verified, are around 8. And the highest unconfirmed redshifts, the ones people argue about and it's not clear if the data is good enough, are about 10. So these are remarkable redshifts because the light has been stretched by the expansion of the universe since the light was emitted by almost an order of magnitude. And so light that may have been in the middle of the visible regime is stretched to near infrared wavelengths. And so these observations have to be made with infrared detectors. Now, what distance does a redshift of 8 or 10 correspond to? Depends on a cosmological model. So you have to know what the amount of dark energy and dark matter and baryonic or normal matter is, plug it into an expanding universe model, and you can convert redshift to distance. And I think redshift 10 corresponds to about 400 million years after the Big Bang, where the Big Bang is 13.8 billion years ago. So we're seeing back roughly 95% of the age of the universe with these most distant objects, which is very close to the era at which we think the first stars and galaxies formed, which is called first light.
The next question is from Harshdeep Singh, who's on with us live, who says, hello, Professor, what is the need for defining the unit of a parsec? They understand the mathematical definition, but not the physical requirement. But maybe some people don't know what a parsec is, so you could talk about that and then why it's necessary.
Right. So a parsec is it's sort of astronomer's distance measurement. It's a natural astronomy distance measurement because it's shorthand for parallax of 1 arcsecond. That's a contraction of that. That's what parsec means, and it amounts to about 3.26 light years. A light year is a physical unit that makes sense because that's the distance light travels in a year. Well, a year is obviously an arbitrary sort of human construction, the time that it takes the Earth to go around the sun, but it's a meaningful unit for humans. So we have light year, and then we have parsec, and a parsec is a couple of light years. The parsec is a useful astronomy distance definition because the nearest objects in the universe are measured by the method of parallax, which is trigonometry. And so parallax of 1 arcsecond means that the object is at sufficient distance that if you form the triangle between viewing the object from one side of the Earth's orbit of the sun and the other side of the Earth's orbit of the sun, where twice the Earth-Sun distance, that baseline, is the base of the triangle, then the apex of the triangle, those two lines going out into a long skinny triangle out into space, that apex is 1 second of arc, or 1/3600th of a degree, so a very small angle. So parallax of 1 arcsecond, or parsec, is a typical distance to the nearest stars. So it's not only a useful unit of measurement because that's sort of how astronomers measure distance to nearby objects by trigonometry, but it also corresponds to the typical star-to-star distance in our region of the Milky Way. So the nearest stars are typically a parsec or a few parsecs away. So it's a very convenient unit for those reasons. So astronomers pretty much use it for talking about distances within the galaxy.
The next question is from Anne Saffer, who's on with us live. The laws of physics say there's just as much reality to the future and past as there is to the present moment. So if the future already exists, what do you think that says about mankind's free will?
Well, the reality of the future is a matter for debate, of course. The arrow of time and the directionality of time, or the fact that time will continue to unfold as it has done since the Big Bang, and who knows if it had existed or it was meaningful before that. That is a fact of physics, but of course since there's no determinism in the laws of physics, ever since the quantum theory 100 years ago, the idea of determinism in the physical universe, Newton's clockwork universe, put simply, does not really apply. And so since we do not have a deterministic situation in physics, there's no way, even with the world's most powerful computers, to play forward the laws of physics, even in a relatively simple physical situation, and predict the future. So since the future is indeterministic, because it can only be assigned probabilities, there is a logical and philosophical skepticism attached to calling the future as real as the present or the past. Because at least you can measure the present with a current experiment, and you can have measured the past with experiments within our lifetime. And in astronomy, you can measure the past by looking out in space and therefore back in time. So in a very practical experimental sense, the future is not as real as the present or the past because it's subject to indeterminism in physics.
All right, thank you, Chris. So the next question is from Rami Ahmad, or Astrogate, who's on with us live, who says, I would like to know your take on the electric universe and how much of it is could be considered science, and could it possibly apply to the solar model, I guess, to the solar system?
Okay, I'm not really sure of the reference here. The electric universe, I presume, is a theory of the universe controlled by electrical forces, so I'm not probably going to be able to answer this question because I'm not sure what that theory is. But it does not sound to me like a mainstream theory of physics if it's a trying to apply the electrical force to understand all phenomena in astrophysics. So I'd have to know more about it to answer that question.
Okay, thank you very much. So the next question is from Achim Steinhagen, who would like to know if there is an understanding of the actual estimated size of the universe.
Yes, again, the universe size depends on the cosmological model, so that depends on our measurement of dark energy and dark matter, and those are fairly mature measurements, even though we don't understand the physical nature of those entities. We have an operational measurement of how the expansion rate of the universe has changed over cosmic time. And that, in turn, and the understanding of the curvature of the universe, the curvature of space-time, allows us to assign a size to the physical universe, which is the observable universe, the region we can see in the history since the Big Bang. And that distance in any direction is about 39 billion light years. So the universe in diameter, if you like, is twice that number. That number, 39 billion light years, is of course larger than 13.8 billion light years, which is the age of the universe in years, because the universe has been expanding faster than light for some first third of its history.
The next question is from Ilsa Martin, who's on with us live, who would like to know more about Lagrange points. They're called parking spaces in space, yet spacecraft in those appear to move. Do they need propulsion to stay in those places? How does that work?
Yeah, so Pierre Lagrange was a famous physicist and mostly mathematician from 18th century France, very brilliant man, actually, one of the greatest mathematicians in history, in fact, very celebrated in his lifetime, and not only the author of Lagrange points, but many other theorems in mathematics. So Lagrange points come from considering the gravity in any system with three objects, like Earth, Moon, Sun being the classic example. Since there's the force of three different objects, in principle, the gravity from those three objects can play against each other such that you can reach a balance point at points between them or away from them. And it's the situation in the four Lagrange points, say, of the Earth. Two of the Lagrange points are unstable, which means it takes energy. That an object placed exactly at the Lagrange point in principle won't move, but in practice will suffer slight perturbations or deviations from its position and then will drift away. And so those Lagrange points need rocket fuel, and those indeed are the Lagrange points that people use. And we have satellites like WMAP, and we have actually a number of satellites and space missions that use Lagrange points when they need to be away from the Earth environment. And in a situation where the gravity is mostly stable and only small amounts of rocket fuel are required to keep them fully stationary at that point. So 2 of the Lagrange points are stable and 2 of them are unstable. And every 3 object system will have these Lagrange points, these gravity balance points. If you had more than 3 objects, things get very complicated. In principle, you can have more than 4 Lagrange points, but we've never been able to study a system like that.
The next question from a live viewer, D. Zach, would like to know if you know what the fastest spinning pulsar is. They've looked it up. Do you know anything about it? Can you talk about what pulsars are and why is it that they spin so fast? This one appears to spin at 716 hertz, so 716 times a second. Do you know anything about that?
Right. Yes, I think that is still the fastest pulsar. There's a category of pulsars called millisecond pulsars, and that's pulsars where the speed is in the range of milliseconds, and 716 hertz is about 1.5, 1.6 milliseconds for one spin. Incredibly fast. I mean, think about that. If this was a physical, it is a physical object. If it was an object sitting in a medium like air, it's not, it's in the vacuum of space, then it would actually emit a tone that's probably a couple of octaves above middle C. Middle C, I think, is 440 hertz. So you're talking about 700 hertz, which is, is higher than middle C on a piano. Amazing physical object that's the size of a small town and the mass of a star spinning that fast. What makes a pulsar spin that fast? Typically because it's in a binary system, and pulsars in general will spin fast. Because remember, it's a star that has angular momentum, like the sun spins roughly once a day. And if the sun collapsed, as it will do to a white dwarf, then conservation of angular momentum suggests that if the sun, shrunk by a factor of 1,000, and as a white dwarf it'll shrink by a lot more than that, then it would spin 1,000 times faster than it is now. So instead of spinning once a day, it'll spin once every thousandth of a day, which is a couple of minutes. So it's not hard logically to see how a star, when it collapses by a large factor, as a pulsar does, it's the second densest object in the universe compared to a black hole, behind only a black hole, will have spin rates that are way under a second. Usually an extra amount of torque in a binary system is required to get the pulsar spinning at the superfast speeds of a millisecond, and so these tend to be in binary systems. We don't know what the physical limit on the fastest pulsar speed is. People still look for millisecond pulsars. There's not that many known. There's maybe only, I think, a few dozen out of probably 3,000 or 4,000 pulsars known totally. Most pulsars have spin rates or periods of about a second down to a tenth of a second. That's where the bulk of pulsars are. So this is the tail, fringe, extreme part of the distribution, the millisecond pulsars.
Thank you, Chris. The next question from a live viewer is from Robert Hartman, who asks, if there is no biology outside of Earth, and we are teaching an astrobiology course, is astrobiology then the same as Earth biology?
Well, if there is no biology beyond the Earth, then it's a very interesting situation because, and indeed, that is a logical possibility that there's no life beyond Earth. We need proof, we need evidence before we can believe that there is. The supposition that there is, of course, is based on the fact that the ingredients for life and the habitable locations for life are fairly abundant in our galaxy and elsewhere. So to many people, it will be surprising if, given the raw ingredients, the materials, carbon-rich material, water, an energy source, a stable planetary environment, and a lot of time for things to evolve, you didn't get biology. But it's possible there's no biology beyond the Earth. And then if there were biology beyond the Earth, is it like terrestrial biology? We simply don't know. There's no reason we should make any kind of argument, even a plausibility argument, that life elsewhere has to be like terrestrial biology, even if it's made with the same ingredients. You can have an information storing molecule that's quite different from DNA and RNA. You can have an architecture of life that's quite different from that of single simple cells that our life started from. You can have metabolisms that are quite different from the metabolism of the cellular life that dominated the Earth for a few billion years. So quite plausibly, life could have a quite different function, form, and architecture somewhere else, even if it was still based on carbon chemistry and liquid water as the medium in which it evolved.
So that relates to the next question from Gage Connors, who would like to know if you have a take on something called astrovirology, and if something like that of studying potential viruses from other kinds of life forms could play a big role in astrobiology in the future.
Yeah, the idea of these kind of entities, pathogens or viruses in space is interesting. It sounds a little scary, of course, because alien viruses, we are unlikely to have any plausible immune response to an alien virus, and so it would likely rip through the planet and just kill and destroy everything. So it's a kind of a science fiction nightmare scenario if alien viruses exist. If life exists elsewhere in the universe or even nearby in the galaxy, then it's likely to be microbial, the most likely forms of life, because the most abundant life on the Earth are microbes of various kinds, bacteria and viruses, most very common. So it is entirely plausible that on alien planets, on exoplanets that have biology, there are viruses. So there are two questions. One, can you detect such life? And the answer is no, we can't. We're not in position to say whether there's life at all on any other planet, let alone to describe it at a microbial level. Now, people have made claims in the past, going back to Fred Hoyle and Chandra Wickramasinghe in the 1960s and 70s, that the spectra of comets and the spectra of some cold solar system objects showed spectral features that were indicative of viruses. That data has been interpreted in a much more mundane way since then. And the problem is that a virus is a sufficiently massive entity, a sufficiently complex molecule, that its signatures spectroscopically are not really unique. It's very hard to say that you're looking at the spectrum of a virus. And so that the idea of viruses in the solar system off Earth has pretty much been debunked at this point. And we are not able to detect them on other planets. And we don't think they could survive in deep space. It's possible in a rock that was ejected from another solar system, viruses or bacteria could survive in the interior of a rock sheltered from cosmic rays or the vacuum of space, and possibly could survive for millions of years. But the odds of a rock being ejected from a planet in another star system and landing on an object in our solar system have been calculated to be incredibly small. So space virology is sort of a hypothetical subject that doesn't really have a subject matter because we've not got any evidence of viruses in space. Even though the idea of those coming to the Earth is definitely worrying, I think it's not anything for practical concern.
Thank you. The next question is from Eric Bjornson. I'm going to make it a little bit more general. The question is, if the shape of the universe is curved, how does this impact our understanding of the degree of gravitational lensing, the quantity of dark matter, and the theory of cosmological inflation? But I'm going to kind of change that to be more like, how does the shape of the universe change those different things, or estimates of dark matter and inflation and gravitational lensing?
Right. So the global shape of the universe is actually predicted once you've measured the amount of dark energy and dark matter in an expanding universe model. And in a universe such as the one we measure, where the composition of the universe is about 2/3 dark energy and 1/3 dark matter, and a small fraction of that dark matter being normal matter, 1/6. Space-time is close to flat, so the universe does not have any global curvature. So it's not actually doing any large-scale lensing at all. In other words, radiation travels through that universe, like the microwaves from the Big Bang, pretty much in straight lines through the universe until we receive them on the Earth 13.8 billion years later. On smaller scales, concentrations of dark matter and normal matter, of course, can cause lensing, and gravitational lensing is a well-known phenomenon. And so that is measuring space-time curvature on a smaller scale, on the scale of hundreds of millions of light years, the size of a cluster or a large cluster of galaxies, or maybe a galaxy itself of sort of 1 million light years, including its dark matter halo. So we do see space-time curvature caused by concentrations of dark matter on those scales. But on the very largest scales of tens of billions of light years, we see no sign of space-time curvature. Space seems to be quite flat.
Thank you. The next question is from a live viewer. Arnold Ginsberg would like to know if there is such a thing as a possible fifth force.
That pretty much comes up in the press or even in the scientific literature every few months, a couple of times a year. I read articles about that. People are looking for a fifth force. Well, the motivation for it is one thing that there was a question about earlier about string theory. So string theory is posited on multidimensional space-time, where there are hidden or compactified dimensions only accessible on very small scales or very large energy scales. So those are hidden dimensions, and possibly there might be a manifestation of one of them, and that would appear as if there were a fifth force, in other words, a force beyond gravity. So the way people look for a fifth force typically is they look for a deviation in the gravity law from inverse square law. So for instance, on large scales, it's possible that gravity deviates from an inverse square law. That's the simple prediction of gravity theory. And if it did, that would be evidence of another force at play. So the simplest way to test for a fifth force is to test the force law of the existing forces of nature. Now, we don't have to worry about the two subatomic forces, the weak and the strong nuclear force, because their force laws have such a very short range. They only operate in the nucleus of the atom. So there's no real way they could manifest a fifth force. Electromagnetism, we could potentially look for a fifth force through that, and most likely gravity, because it's the weakest force. And so if there was an unnoticed fifth force in the universe, it's probably a weaker force on our energy scales accessible to us than gravity. And so you look for a deviation of the gravity force law. People have claimed that kind of a deviation of the force law on various scales, sometimes on small scales as well as large scales. None of these has withstood the test of time or corroboration by other groups. So at the moment, there's no evidence for a fifth force, although it is theoretically still an interesting thing to do the experiment to look for it.
The next question is from Brandon Kelly, who's on with us live. And the question is about the deep field picture from Hubble. Why doesn't NASA double the exposure time for the ultra deep field picture? Surely they could see even further back in time. So why haven't they done that?
Well, they did. So the original deep field, the original Hubble deep field, was done, it's over 20 years ago. I think it was the mid-1990s, so almost 25 years ago now. And the ultra deep field was more than a doubling of the exposure time of the deep field, and it actually was done with a different imaging camera, with the ACS camera. So there was a better, Hubble had been refurbished between the deep field and the ultra deep field. And now, of course, because you don't want to have all your eggs in one basket, and what if that one region in the sky you looked super deep was not typical for some reason? You want to spread your bet. So rather than go deeper for a while, the astronomers put that extra time into a second field at the same depth in a different other half of the sky. And that helped ground-based astronomers because one of these fields would be in the north and one would be in the south. So the Hubble Deep Field North was followed by the Hubble Deep Field South, and so on. The question of whether you could just keep going and try and double the exposure time it's not an unreasonable thing to do, but there are two problems. The first is that you end up with diminishing returns. Well, it's also very expensive. I mean, so the astronomers that try to do science with the Hubble Space Telescope using smaller allocations of time, like a dozen orbits or 24 orbits, they get kind of bent out of shape when the project puts hundreds or 1,000 orbits into one ultra deep exposure. It may well serve, more than a handful of scientists, but it doesn't serve the science of a lot of the Hubble users. So there's a little bit of tension there between putting too much time into deep fields. But probably the more basic reason that it's not done is diminishing returns. And that's diminishing returns in two ways. It's diminishing returns because you're reaching pretty much the sensitivity of the instruments on the Hubble Space Telescope. Going from the deep field to the ultra deep field benefited from a new camera with more sensitivity, but the cameras are almost as good as they can get now. So there's apart from the fact that Hubble is sunsetting and it's not going to get new instruments, there's no real way to see deeper with your instrument. And the second is that at the density, at the depth that the ultra deep field and the best deep fields are going, the sky is so littered with galaxies and faint galaxies that they start to overlap and bleed into each other. In other words, there's almost no dark space or black background between the galaxies. And that makes the image analysis of these very deep images really challenging. So if you continue, it's called the confusion limit. This is a technical term in astronomy for this, which sounds obvious because confusion is confusion in English too, is when objects are so proliferating that along one sight line that they overlap on any sight line, then you can no longer distinguish individual objects easily, even with a clever algorithm. So the confusion limit and the diminishing return is the real reason it's not worth going much deeper than we've gone.
All right, the next question is from Robert Hartman, who asks, can stars split and form two or more separate stars?
Definitely. In the star formation process, stars rarely form singly. The most likely in our study of the Milky Way star formation regions, stars tend to form in groups and clusters. The Orion region, which you can see with the naked eye, the Orion Nebula, which is a sort of nursery of young stars, is a really good example. At the heart of the Orion Nebula is the trapezium cluster or trapezium formation, and that's 4 young protostars. So there you have a very small region of space where 4 stars form very close to each other. So since stars really do not form singly, they form in little dense knots that gravitationally collapse separately and form individual stars. Various things can happen. Sometimes a star forms that's very massive and essentially it splits apart, as the question was implying. So you can definitely have a star that just as it forms is unstable and it splits into 1 or 2 or more smaller objects. You can also have a small region of space where most of the mass goes into one star and there's a little left over for another star or a third star, and the interaction between those stars ejects 1 or more from the system, giving the appearance that maybe only 1 star or 2 stars formed when actually there were more there originally. So the interactions between multiple young stars in very dense regions of space where they form can lead to all sorts of interesting effects.
Thank you. The next question, actually, we've got several people are interested in the same kind of thing. So one question is, what do you think of the possibility of discovering another large planet in the solar system? And then a related question is there any update on planet 9 or 10 or whatever it is at the edge of the solar system?
Right. The odds of finding another large planet within the core solar system, by which I mean the volume out to Neptune, are essentially 0. These orbits are measured so well that any object even of the mass of the moon, say, so a large moon type mass in that volume of space would perturb or nudge or influence the orbits of the main planets. We really measured them very accurately. So that's essentially ruled out. And so we've essentially ruled out everything down to a small little moon. So it's possible, and one of the major planets ejected one of its moons early on, and it's floating around in the solar system. We might not know about that. But as far as a new planet, no, it's very unlikely. Planet 9, or another planet in the regions beyond Neptune, where Pluto is, dwarf planets, and there are several other dwarf planets, as we know. So this is called the Kuiper Belt. So the region that ranges out to about 40 astronomical units, 40 to 80 astronomical units, is called the Kuiper Belt, named after Thomas Gerard Kuiper, who is a famous planetary astronomer across the street from me in the Lunar and Planetary Lab at the University of Arizona. He had earliest evidence that there were small objects out there, very few known back in his day. Now we know of thousands of them seen through telescopes. They're mostly small. They're mostly asteroid-sized objects. It's possible there are a handful of Pluto-sized dwarf planets out there, and people are looking for them actively. But again, it's almost impossible for there to be anything the size of Neptune or Uranus, so the size of a gas giant out there in the region beyond Neptune, actual Neptune, because it would perturb the orbits of Neptune and Uranus, and we don't see that.
All right. The next question is from a live viewer. The Anish would like to know, what is randomness? Are we able to understand randomness, or why are we still not able to completely understand randomness? Is this a real thing in the universe?
Yes, randomness is a phenomenon. It's a physics phenomenon, and it's a mathematical phenomenon. So we can see processes that we think to be random, and they're typically the most obvious examples are those that occur in gases or in systems with large numbers of particles subject to thermodynamics. So thermodynamics is a typical situation where motions of the individual particles or objects are random. They are random in velocity potentially, and certainly random in direction. So that randomness exists in a gas, or it exists in any similar type situation, and that's down to standard thermodynamics. We also see other situations where randomness applies even though there's an underlying regularity. So you can have a situation where there's periodicity in the behavior, oscillation or vibration, but where there's randomness on top of that periodicity, or noise. Noise is of course random too. So when astronomers talk about noise, they're typically talking about a random process or signal that applies to something they can measure, like a position or a temperature or a velocity. So yes, there are various regimes where astronomers definitely measure random behavior, and they can even exist in systems where overall there is some regularity.
All right. The next question is from Lawrence K., who would like to know, how bad is the situation with all of the accumulated space junk in low Earth orbit? How does this affect ground observations or collisions with space telescopes, that kind of thing?
Yeah, the space debris problem is getting a lot of attention, and so it should, because it's a big issue. So low Earth orbit is very cluttered. I mean, the space age is just not much more than half a century, and thousands of objects have been put up there. And it's not really the thousands of objects that's a problem, it's the handful of them, and it's not really that many, that have broken apart or been destroyed. And in one really egregious example that is infamous, a few years ago, China blew up one of its own satellites, pretty much as an experiment, and created instantaneously a huge amount of space debris in low Earth orbit. That was one of the most antisocial acts ever in the history of the space program. So some space junk has just happened by gradually launching things into space that degrade or fall apart. Occasionally there's a deliberate creation of space junk. And so even for the space station, as is well known, that the space station is not in the very lowest Earth orbit. It's up, lowest Earth orbit's about 150 miles, but space station's up at 250 or 300 miles. Even in that somewhat higher low Earth orbit, as it's well known because it gets into the news, about once a year, maybe even more than once a year, the astronauts have to hunker down in the thickest part or most shielded part of the space station because there's a known piece of debris, usually that's in the vicinity, which would have an impact speed high enough to punch a hole in the space station. And remember, these pieces of debris, they don't have to be big at all. They certainly don't have to be the size of a coin. They could be more the size of a pinhead because they're moving so fast. So space debris of all sizes is not cataloged because it's impossible to do that. It's known to be increasing. The biggest concern now is, of course, the launch of nanosats and microsatellites, because it's so cheap that with these constellation clusters of satellites that are going to be used for position sensing and telecommunications, companies like SpaceX just single-handedly are going to launch literally tens of thousands of nanosats within the next decade or so. And the nanosats themselves have a concern to astronomers because they're going to create glinting or reflection that'll be seen near sunset and sunrise in the sky, and so mess up astronomers' dark sky, but also the likelihood that over time some of them will fall apart, or they'll collide, or they'll degrade, and leave even smaller pieces of space junk in even larger numbers. So the space junk problem is not going away. NASA's entertained solutions, sort of electromagnetic sweep mechanisms to try and collect it, But the math is very inhospitable to these solutions, because even if we're talking about a relatively slender zone of low Earth orbit, the amount of real estate around the surface of the Earth, you can work out in how many square miles of real estate you have to cover with a sweeping mechanism. It's really beyond any technology we have available to us. So no one really has an answer to space junk at the moment, but it's a growing problem.
All right. I think we'll take a couple more questions. The next one is from Robert Hartman, who's on with us live, who would like to know if it would be possible to bring organisms living in extreme conditions on Earth to a different object in space, like Io, Mars, Titan, or something like that, and do a test to see if it will survive.
It's possible. It's actually something NASA has decided it will not do. And this has arisen most notably with Mars, because NASA has a series of Mars missions planned that will eventually bring back samples and then later end up with the human habitation. And NASA's decided to be very conservative. They decided that they don't want to forward contaminate Mars. So regardless of whether Mars has life at all, or has ever had life, or has no life on the surface but might have underground, they don't want to take the risk of seeding Mars with life, alien life, and therefore altering it fundamentally and possibly forever by biocontamination. So NASA has taken a very strict view of planetary protection, and of course even stronger view of contaminating the Earth with microbes brought back from space. The private sector, however, has no such qualms and is unregulated in terms of what it does. And so it's quite possible that SpaceX, Elon Musk, might go to Mars, and they may try and seed the Martian soil with extremophiles and see how well they do, as potentially a way to make a habitable part of Mars under a bubble dome, say. You can't terraform the whole Mars. That would take a long, long time. But you might be able to terraform a part of Mars in a protected environment. And doing the same for other solar system objects like Io or Europa is also possible. But I think at the moment, we're still mostly interested in whether they have extremophiles themselves, so whether there are native extremophiles on these planets. So well before we take our extremophiles and risk compromising the experiment, we're going to make sure we go there clean and see whether they have extremophiles already.
All right. The next question is from live viewer DevWriter. Asks, will the speed of the expansion of the universe ever approach the speed of light? And so that light from distant galaxies will never reach us anymore.
Yes, that's actually a projection of the current cosmology. So the current cosmology has dark energy as 2/3 of the mass energy ingredient of the universe, and dark matter is 1/3 of the ingredient. Because dark energy is dominant, now we're situated in an accelerating expansion. And as excuse me, as that acceleration plays forward, the density of dark matter will decrease, and so the influence of dark matter will recede, and dark energy will become even more dominant. So if we play forward the expanding universe, in a few billion years, dark energy will account for 95% of the mass energy of the universe. And at that point, the accelerating expansion will increase. And yes, there is a time, and it's a little uncertain, but it's a few tens of billions of years, when the speed at which every point in space-time is expanding from every other point in space-time is faster than the speed of light. And at that point, we'd stop. We'd have an inability to see any objects further away in space. We'd be stuck just viewing the objects that happen to be really near us before the universe expanded that fast.
All right. The final question that we are going to be able to take today is from Ryan, who would like to know, so dark matter gravitates and condenses on galactic scales, but we don't seem to get smaller scale, superdense dark matter black holes, for example. Do we have any ideas about why it behaves that way?
Actually, dark matter does condense on various scales. So there's what astrophysicists would say is there's a power spectrum of density fluctuations in the early universe, and we believe that power spectrum, or the amount of energy in overdensities on different scales going as a power law, was seeded by inflation. So that's based on initial conditions. But that actually means that there are fluctuations of density in the expanding universe that propagate down to smaller scales. So dark matter does not just clump on galaxy scales, but actually on smaller than galaxy scales. And one manifestation of this is the fact that in simulations, if you look at a galaxy in a simulation, the entire galaxy is within a dark matter halo, but there are many, many subhalos of smaller mass, the masses of maybe the mass of a globular cluster, say, in the halo of a galaxy. So dark matter simulations show this subclumping of dark matter on smaller scales, many clumps, not maybe going down to black hole mass, but going down to masses of 1,000,000 or 10,000 or 1,000 times the mass of the sun. So it's very interesting that the simulations show that. And the question is, what do the observations show? So we don't tend to see visible objects associated with these hypothesized dark matter clumps on small scales. One of the ways people are trying to show that they exist anyway is through microlensing. And there's pretty tantalizing evidence, I don't think it's nailed yet, but from a couple of different research groups that show microlensing sensitive to dark matter clumps on small scales have found that signature. And so they think they really have proven that dark matter clumps on much smaller scales than galaxies, as would be expected by the theory and by simulations, so it's reassuring. Thanks for your questions on very many topics as usual, and I think we'll be talking to you again in the new year, 2020. So everyone have a good holiday.